Friends, today I am going to show you how to use limit analysis to model the anisotropic David Christian yield criteria uh, by using my codes. So you can refer to this paper, Kinematic Limit Analysis for Clays with Anisotropy and Different Strains in Compression and Tension. This is my paper. In this paper, I have given the formulation for doing upper bound limit analysis of David Christian yield criteria. This yield criteria have mainly three parameters A, B, and H, which is correlated to under shear strength in cohesion, under shear strength in tension, and under shear strength in shear. If these three are equal, then the soil is isotropic. But generally, this does not happen. In case of soil, the underrated shear strength in compression is much higher than underrated shear strength in tension. That's why the anisotropy arises. And okay, so now I'll show you how to do this analysis. I have shared with you the 3D limit analysis code. You can see here inside that in anisotropic, this is DC anisotropic. Okay. If you have MATLAB and Mosaic is installed inside the MATLAB, now I am opening this upper bound code. So here I will show you this upper bound code. We can use different kind of meshes, like here is the coarse mesh, medium mesh, or fine mesh, and it is a very fine mesh. So currently I will do the analysis by using very fine mesh. And I have generated the mesh in such a way that the mesh will be very fine near the footing, and it will gradually, the mesh size will increase when it goes to boundary. And okay, in this code also I will explain you how to plot the mesh and how to plot the velocity field in 2D, and how to plot the plastic flow, and how to save the all these things in MATLAB file. Okay, first I will show you how to run. So I have opened the file, this upper bound file. Now if I'll run, so it will take some time because it is a very fine mesh. So after some time, we'll just wait. Okay, in between I will show you what parameters I have used here. Okay, for this case I am analyzing um, for isotropic case. So you can see here everything is under shear strength in cohesion, compression, and tension, and shear, all are one. If all these are same, then this is an isotropic case. So I'm analyzing for an isotropic case, and you can see the result I got is 5.17. This is slightly upward bound than the original result 5.14, original analytical result. So it is a very good approximation of the analytical result. So I'll show you how to, okay, we'll see how the mesh pattern is. So I'll uncomment it. So you can check. Okay. And yeah. So this is the plot of mesh pattern. Okay, so up to, I think up to 1, this is the mesh size distribution. This is according to, as I have explained before. Then if you want to plot the velocity field, so you have to uncomment this part, uncomment, copy, and paste here and run. So you can see how the velocity distribution is. Okay, so if you want to see the plastic flow, you have to do comment, copy, paste. Okay, this is the plastic flow distribution. So you can make it the figures much suitable to visible by changing these contour limits. And you can do this. You can see here I'm using cont plot, and the file I have shared in that. There is a file named contour plot, and here you can do the modification and you can make the figures much better also. And for saving this the figure files, I am using this command. So okay, this is for as I have told, this is for isotropic case. And I have also mentioned here, if you want to make the DC yield criteria to make the DC yield criteria anisotropy, then you have to change the actually B by A ratio. You can see here here. So here the parameter B by A ratio, I have for the this case the B by A ratio is 1. The B by ratio is changes from 0.5 to 1.2, and that indicates that represents the anisotropy in this yield criteria. So I will check it. Suppose here actually in this code, this is the ratio B by A actually. If I am changing this to suppose 1.2 as it is mentioned, the range is from 0.5 to 1.2. We'll see what is the result we are getting. Okay, so it will take some time to run, and in between we will see what is the result of 1.2 if it is directly available. Okay, maybe it is mentioned here. It will be almost 5.5 knot. Okay, for 1.2. Okay, so the result is 5.5 knot. Okay, so yeah, the result is 5.5 knot. Okay, this is for upper bound case. So now we will see in that folder also in 3D limit analysis anisotropic and DC anisotropic folder, you will get the lower bound code also. Although here I am using a different mesh, you can change the mesh accordingly. But what I want to mention that this is for isotropic case because here everything is 1. And if I'll run it for lower bound, the value I'll get, okay, yeah, the analysis is done. It is very fast. And the analysis result is 5.136, which is very close to 5.14. And suppose I want to run for an isotropic case, as we have done there, it is nearly 1.2. If we will run for 1.2, it should come nearby 5.5 knot. Let's see what is the lower bound result. Yeah, so the lower bound result is 5.457, which was the upper bound result was 5.5 knot. So this is working very well. So if you want to plot the stresses, the stress ratio, like okay, then you can do this by using cont plot M. So the stress ratio, if I plot the contour plot M, you can check here, I think, yeah, this is the stress distribution. And when it reaches to 1, all these things are in plastic zone, and when it is less than 1, all the so in this region it is mostly in elastic zone. And okay, you can check all these things. Okay. Okay, thank you. I think now you will be able to run the DCILD criteria for anisotropic cases easily. Thank you.